So last few days, okay, everything's been about work energy theorem, okay? And work energy theorem deals with situations where our final energy does not equal our initial mechanical energy. Okay? The reason they're not equal to each other is because in a work energy theorem question, work is being done. At any time work is being done, there's a change in mechanical energy, meaning those two things are not equal. Everyone follow me on that? Okay? In a law of conservation of energy question, no work is being done. If no work is being done, then there's no change in energy, and our initial mechanical energy and our final mechanical energy will be equal. Right, so these are the roller coaster questions like you would have done in Science 10. That's a law of conservation of energy problem, okay, where there's no friction, there's no forces taking energy away or putting energy in. The energy at the top of a hill is equal to the energy at the bottom of the hill. Okay? And in the perfect physical world, that would be true. Since we don't live in the perfect physical world, we go over work energy theorem first, because that's how things usually work. Okay? Everybody follow me there. So this stuff should hopefully seem familiar and be fairly review-like for you. All right, big thing we have to understand, because this is the law of conservation of mechanical energy. Energy cannot be created or destroyed. Okay? It is possible for it to look like there's less energy at the end of something than there was at the beginning, but that's only because it was used to do work. Okay? It means it got turned into some other form of energy. It's still there, it's just not mechanical energy anymore. Okay? So energy can't be created or destroyed. The amount of energy is always the same. Okay? Understand that energy can be converted from one form to another. That's what we just talked about. Sometimes it looks like the mechanical energy isn't conserved, but that's just because it's being turned into something else. Right? And lastly, use this concept to calculate other variables related to the mechanical energy of an object, okay? And that would be like in a roller coaster question, and we'll go over a few of those here today. Okay. Mechanical energy is made up of two kinds of energy. They are kinetic and potential. Okay? You have potential energy you have gravitational potential energy if you are above the Earth's surface. If I'm standing on the Earth's surface, I have no potential energy because I'm on the ground. Okay? I can't get any lower than that. Right? But if I'm raised above the Earth's surface, then I can fall. I have potential energy. Okay? It would take work to get me to that point. Okay? The other type of energy is kinetic. If you're moving, you have kinetic energy. Everyone all right with that? Okay? And we talked about yesterday how the faster you're moving, the more kinetic energy you have. In fact, exponentially more. So if we're looking at this kind of situation, we've been dealing with work energy theorem, which looks like this. Work is equal to the change in mechanical energy, final minus initial. In a perfect system, that number will come out to 0, because EI and EF will be equal. In all the situations we've dealt with thus far, they were not equal. So we took the final mechanical energy, and we calculated that by adding the kinetic energy final to the potential energy final, and then we subtracted the kinetic energy initial plus the potential energy initial. So this was our final mechanical here. This was our initial mechanical. We subtracted them, and we got how much work was done against non-conservative forces. Non-conservative forces are things like friction. They make it look like energy is being lost. And it is. Mechanical energy is being lost, but it's being turned into something else. Okay, in a roller coaster situation, at the top of a hill, I would have a lot of potential energy because I would have a lot of what? Height, right? Potential energy is based on basically three things: mass, acceleration due to gravity, and height. So the higher above the Earth's surface I am, the more potential energy I will have. Gravity's not going to change, so if I went to another planet and I was at the same height as I was on Earth, I would probably have a different amount of potential energy. Like for example, if I'm standing on top of a 3-meter ladder on Earth, I have a certain amount of potential energy. I stand on that same ladder on the moon, I have considerably less energy. Okay? Because if I fall off that ladder on the moon, I probably won't even get a bruise. Because I won't reach the same speed by the time I hit the ground on the moon, because G would be smaller on the moon than it is here. Okay? Everything else would be the same, still me, okay? Still falling the same height, but because I wouldn't reach the same speed, I don't have the same potential energy. Does that make sense to everybody? 1/6 of Earth, so about 1.6 something meters per second. Yeah, this. And that's why if you ever watch any of the moon landing footage, it almost looks like it's in slow motion. Okay, when they're moving around, okay, they look like they're in slow motion because as they walk, they actually kind of come up off the surface a little bit. All right. Up here, I would have a fairly low amount of kinetic energy because I probably wouldn't be going very fast at that point. Okay, it's the highest point on the ride. Down here, at the lowest point on the ride, I would have my minimum amount of potential energy. Probably I would have 0 potential energy. I can't really go any lower than that on this track. Okay, but I'd also be going faster here than anywhere else on the track, so I would have my maximum amount of kinetic energy. Okay, if I went over a little bump after that, I'd get a little more potential energy because now I'd have a height again. Okay, but as I go up that hill, my potential energy, or sorry, my speed will slow down, and I'll have less kinetic. So basically what's always happening in this kind of situation is potential turns into kinetic and vice versa. Right. At the top of the hill, lots of potential, very little kinetic. As I go down the hill, the potential becomes kinetic. Okay? As I go back up the hill, the kinetic becomes potential. They turn into each other all the time. Everybody all right with that idea? Right. So in other words, in a perfect world, the final mechanical energy is equal to the initial mechanical energy. Okay, so consequently, the total mechanical energy remains constant along the path between initial and final points. It doesn't vary. Okay? So if I was looking at this and I was able to change these graphs here, okay, this stands for total mechanical energy. Would that ever go up and down? No. Okay. Would these two go up and down? Yes. Okay, here the potential energy would be very high, the kinetic energy would be very low, and as we go down the hill, okay, this one would go up, this one would go down, okay, and this one would stay the same. Okay, all the way along. All right, something else we need to consider about mechanical energy. Is energy vector or scalar? It's scalar. Okay, so do I have the same amount of kinetic energy if I'm moving at 20 meters per second vertically or 20 meters per second horizontally? Is my amount of kinetic energy the same or different? It's the same. Okay. Kinetic energy is dependent on your mass and your speed. Okay. It doesn't matter which direction I'm going. If I'm moving at 20 meters per second, I have the kinetic energy that belongs to 20 meters per second. Okay? It doesn't matter which way I'm going. This is a mistake people make if I give them a question about law of conservation of energy where, like, something's dropped out of a plane. Okay? So I've got a plane moving this direction. If I drop something out of that plane, it's moving at the same speed as the plane, and it's moving horizontally, at least at time 0. Okay, everyone all right with that? But people forget that that speed applies to its energy because they don't picture it falling downwards. Okay, it's not falling downwards yet, but that doesn't mean it doesn't have kinetic energy. I'm moving horizontally, I have kinetic energy. Okay, energy is scalar because kinetic energy is based on speed, not velocity. All right. Now, I'm a nerd, and I can live with that. That's who I am. You have to be comfortable in your own skin. Okay? A number of years ago, took the track team to track Provincials, and this device was at the shot put area. Okay? And I lost my you-know-what because I was like looking at this thing, and because I'm also a physics guy. And I went over and grabbed the whole team, and I'm like, you guys have to come over and see this. And they really thought I was crazy. You're looking at me with the same look they looked at me with. Crazy Blair. It's a ramp. I know, but you have to consider how this ramp works. Okay? If you put a shot put at the top of this ramp, any shot put, doesn't matter whether it was like the junior women's or the senior men's shot put, all different sizes, if you put it at the top of this ramp, it would roll down the ramp. That's not the cool part. Because it would obviously roll down the ramp. Okay? But as it rolls along this level piece here of metal track, it slows down. It slows down because of friction. It doesn't matter which shot put you put here, as long as you put it at the top and don't roll it, like just let it go. By the time it got back to the throwing area over here, it would slow to a stop. Nobody could ever hurt their fingers like at the bowling alley. Okay? And if you've ever been to the bowling alley, you probably saw some kid get their fingers squished between the bowling balls when they come back in. Okay? You never had to worry about that with this because it was designed to have enough energy lost to friction along the length of this that it would stop any shot put that was placed here. Okay? Because remember, friction is also based partially on the weight of the object that it's acting on. Okay? So it affected all the shot puts equally because if I have a smaller shot put, it has less energy when it's sitting there because its mass is smaller. So it didn't matter which shot put they put here. Okay? Any shot put would roll to a stop by the time it got to the end. Okay? I'm sure less than 1% of people notice that when they look at that thing and they're just like, yeah, that's how they get the shot puts done. This is the world you're going to get into when you really start to understand physics. Everything looks different. It's not as frightening. The point of that thing is to not have to have people carry shot puts through the throwing area where they could get a shot put in the brain. This is safer. Right? So they retrieve the shot put, they put it on this ramp, it rolls back, and they stand back where no one's going to hit it. You throw a big, heavy metal ball. The person who throws it the furthest wins. Track and field is very simple. Most of the events are very simple. Throw it farther, run faster, jump higher, farther. It's all very easy. It's not like golf where the person who takes the least shots wins. Highest score loses. No. Anyway. Okay. So, does that sort of make sense? Okay, so this is an example of law of conservation of energy. They had to figure out how much energy the object would have or would lose along this length and make sure that they made a ramp tall enough that they would all have that amount of energy when they were at the top. Okay, so it had to be designed and calculated that way. That was the brilliant part of it. Okay, that somebody actually went to the bother of doing and actually figuring it out. Okay. Now, this has all kinds of real-world applications. Okay, back in 2010, when the Winter Olympics were in Vancouver, okay, they had a big issue with one of their skeleton tracks. Okay, skeletons, like for people who like luge but are even crazier, right? Because you go down the luge track head first, because it's not exciting enough if you go down feet first. Right? You have to be crazy to go down head first. Okay? But what happened, tragically, was they got more rain than they had anticipated, and it made the track a lot slipperier than they had accounted for. And during one of the practice runs, one of the skeleton riders went off the track and was killed. Okay? Because they had too much energy going into the corner, because there was way less friction than had been anticipated when the track was initially designed. Okay? So when he got to the first corner, instead of going up on the corner and traversing the corner safely, he had so much energy that he slid right out. Okay, and went right over the top and was killed. Okay, so they couldn't redesign the track. The Olympics started the next day. What's the easiest solution to that? Well, they couldn't really change the friction either. It kept raining and making the ice really, really slippery. And friction would have been difficult to keep equal for all runners, or for all people on this track. So what's the easiest way to make sure nobody goes over that edge? Have them start. Exactly, have them start lower. Okay? The only reason he went out and over the corner was because he had too much energy by the time he got there. So if I start them a little bit lower, they'll have less potential energy at the beginning. they'll have less mechanical energy at the beginning. In fact, they'll have less mechanical energy everywhere, all the way down the track, which means you wouldn't have enough mechanical energy or kinetic energy to go off the track on that plane.
Why would they put a roof on that?
Because if you put a roof on it, they can go upside down, which could give them gravity advantage. Something with the designs of the track. Right? They already have high walls. It's like a water slide, right? The corners always have the high walls.
Like they could have made a roof without like actual walls instead of pillars.
Like a cage?
It's like a roof with like pillars.
Okay, if I put a pillar in the middle of the track, I'll kill somebody anyway.
On the side.
Okay, how does it, I'm sorry, I'm trying to engineer this. How do I get a pillar here that puts a roof here?
It's the one on the side.
So I do this.
And fly off the track.
If someone flies off the track, it hits the roof.
No, because then the rain will go on the track.
But the track has to be wet though. It has to be icy.
It could freeze it.
It doesn't work that way.
So
You're talking about re-engineering something to put away, right? They didn't have time to re-engineer the track in one day. The simplest solution was start everybody lower where they have less mechanical energy. I'm not arguing that, yes, we could have done things to re-engineer the track, but there was a time crunch. The Olympics started the next day. There wasn't time to re-engineer the track. Okay? The easiest thing to do is just say, don't start so far away. Okay? Start a little lower where you don't have as much energy.
but then they could have fallen off on another area.
No, the other areas were fine. It was that corner in particular that was the problem. They didn't realize it. It was during a practice run that they got that this happened.
Did they test the other one back there?
Yes. Okay, so what we're looking at here, guys, is that at the beginning of this thing, if we're in a bobsled, at the top of this track, at the beginning, if we don't push it, we have no kinetic energy. We have 600,000 joules of potential energy. We have 600,000 joules of mechanical energy, right? Because it's the sum of these two. A little further down the track, we'll have converted some of that potential energy into kinetic, but we'll still have 600,000 joules of mechanical energy. Okay, and that's true all the way down the track. All that changes is how much of it is potential and how much of it is kinetic, because they keep turning into each other. Okay, potential gets converted into kinetic, which is why reducing the height they start from reduces the amount of kinetic energy they can have and the amount of mechanical energy they can have at any point. All right, so we got a motorcycle wanting to leap across the Grand Canyon in the figure shown by driving horizontally off a cliff. Okay? A guy actually did this.
What?
Yes. Evel Knievel. Over the Grand Canyon. Not the wide. Right? It sounds impressive when you say jump the Grand Canyon, but he picked the narrowest part. Okay? So, he jumped over the Grand Canyon on a motorcycle. I'm going to show you the video of it, actually. Okay? Just a second. Now, what we want to try and figure out is how fast the motorcycle would be going when it lands on the other side. Okay? Now, he did this the right way, in that he jumped from the high side to the low side. Okay? You don't want to do this the other way, because you'll do this. Okay? And that's not going to work out very well. Okay? Well, he didn't keep a hold of it, no. Yeah. Evel Knievel and his son Robbie Knievel did a lot of really stupid crap and like broke every bone in their bodies at some point. Okay, like one of them jumped over a bunch of buses, school buses in a line in Vegas, and like they just did some crazy stuff. Okay, one of them was he tried to jump over another canyon on a rocket, or with a rocket, and as the rocket launched, the parachute deployed. And so the rocket's trying to produce thrust, but there's this big parachute producing drag behind me. Ended up in the river. Like this, yeah, all kinds of stupid stuff. People do stupid things, and they get on TV for it. Do you see the problem?
The dumb die young.
Not young enough. Okay? Otherwise, the stupid gene would be eliminated by natural selection, but it doesn't seem to be.
The dumb make history.
The dumb make history. Yeah. That's really scary. Yeah. All right. So if we're looking at this example, okay, we want to figure out how fast the motorcycle is going when it hits the canyon on the other side. Okay, so when he lands on the other side. Okay, what do we know is the same here and here?
Mechanical energy. Mass.
The mechanical energy, the mass, okay, those things don't change, okay, but more importantly, the mechanical energy of the motorcycle is the same on this side as it is on this side. Obviously, over here, more of that mechanical energy will be in what form? Kinetic, okay, whereas over here, more of it is going to be potential. If we want to calculate how fast the motorcycle is going over here, okay, this is how we set it up. Okay, so we say, first off, that the mechanical energy, initial and final, are equal. Okay? Then we expand that out. All right? So initially, we're looking at some potential energy, some kinetic energy, and on this side, same thing. We're looking at some potential energy and some kinetic energy. Everybody with me there? Yes? Okay. Do I have formulas that calculate all of these? Yes. All right, so I'm going to have m times g times the initial height plus 1/2 mass times the initial speed equals same thing on this side except with the final values, final height and final speed. Now, what I'm looking for is that number. I'm trying to figure out how fast the motorcycle is going on the other side. What am I never told here? The mass of the motorcycle. Do I need it? I don't, because it doesn't matter. The only thing that's acting on the motorcycle here is gravity. Does gravity act on everything equally? Okay, so mass doesn't matter. This could have been a garbage truck instead of a motorcycle, and the number would still be the same. It would go the same speed on the other side, okay? Because gravity is the only force doing anything here. Okay? So what I can do, from a mathematical perspective, I can cancel out all the m's because every one of my terms has m in it. Okay, so they're all affected by it the same way. So I'm going to take out all the m's, which is good because I didn't know what m was anyway. Okay? And I can do that as long as I'm not looking for any form of energy. If I'm looking for speed or height, okay, they're not dependent on the mass. Energy is. Okay. All right, so now I've eliminated that. I'm looking for VF. What do I do with this? Subtract it over to the other side. So I'm going to have GHI plus 1/2 VI squared minus GHF. Okay, and that's going to equal 1/2 VF squared. Really, what we're saying here is this. Right? Our initial potential plus our initial kinetic minus our final kinetic equals, our final potential, equals our final kinetic. Okay? That's effectively what we're saying. Is everyone okay with that? I want to get VF by itself. What do we do with the half? Divide it. Okay? And then what? Square root. Okay? So that's going to get me VF. All right, so you would have done a lot of questions like this in Science 10. So I'm going to have 9.81 times the initial height, which was 70 meters. Okay, so times 70 plus 1/2 times 38 meters per second, and that's squared, minus 9.81 times the final height, which I think was 35, right? Divided by 1/2. So 9.81 times 70 plus 0.5 times 38 squared minus 9.81 times 35 divided by 0.5, all square rooted. All right, when they land on the other side, they'll be moving at 46.2 meters per second. Okay, which is pretty fast. It's 166 kilometers an hour. Okay? It's pretty hard to keep control of your motorcycle when you come crashing down at 40-some meters per second. Okay, so that's why you fell off, obviously. All right, is that ringing a bell? Looking familiar a little bit from last year? Okay, so this is kind of just the reasoning of what we just did. Okay. All right, I want you guys to see if you can calculate these two things. Okay, these are actually quite a bit easier than what we just did. All right, I'm going to give you a couple minutes here to see if you can figure out what the initial mechanical energy is and what the gravitational potential energy is in the second instance. So we have a frictionless roller coaster car. We know its mass. Okay, its mass is 800 kilograms. Okay. At one point on its journey, the car has a speed of 4 meters per second and is 35 meters above the ground. All right, so I'm going to say that that's VI, okay, the 4 meters per second, and HI, 35 meters. Okay. Later, its speed is measured to be 20 meters per second. Okay, so I'm going to say that that's going to be VF then, because it's later. Okay, calculate its total initial mechanical energy relative to the ground. Okay, how do I calculate mechanical energy? Potential plus kinetic. All right, so my initial mechanical energy will be the initial potential energy plus the initial kinetic energy, which will mean m times g times h initial plus 1/2 mv initial squared. Okay, do I have all those numbers? Yeah, I do. So 800 times 9.81 times 35 plus 1/2 times 800 times 4 squared. Okay? That should give me my initial mechanical energy. Now, I keep saying initial mechanical energy. Do I need to bother saying initial mechanical energy? No, because the mechanical energy is not going to what? It's not going to change. Okay? There's no work being done here. All right, so we're going to have 800 times 9.81 times 35 plus 0.5 times 800 times 16, 4 squared. All right, so this thing has 281,080 joules worth of mechanical energy at any point. Okay, and it's important for us to remember that that's the number at any point, because that's important for B. Okay, in part B it says, what's the gravitational potential energy in the second instance? Okay, well, can I still use that formula? Yep. Except I'll replace all the i's with, okay, so what's true here in the second instance is this. The final mechanical energy, which is that number, equals the final potential plus the final kinetic. So if I want to find the final potential, what do I do with the final kinetic? Subtract it over to the other side. So I'm going to have my final mechanical minus my final kinetic, and that'll give me what the question's looking for, my final potential energy. So 281,080 joules minus 1/2 times 800 times 20 squared. Holding the speed in the second instance. If I do that, I should be able to calculate that. So subtract 0.5 times 800 times 20 squared. Okay. So it is 121,080 joules worth of potential energy here. How high above the ground is it? Calculate it. That's the potential energy when it's moving at 20 meters per second. Calculate how high above the ground it is when it has that much potential energy. Okay, so that's what we know. Potential energy at that point is 121,080 joules. Do I have a formula that calculates potential energy? Can I calculate my height? Yes. What do I do with M and G? Divide them over. All right, 15.4 meters off the ground. Questions on that one? Okay, I want you guys to try 1 and 2. I'll make this bigger so you can actually read it. Okay, I want you guys to try 1 and 2 for right now. Then we'll look at number 3. Number 3 is like the mother of all law of conservation of energy questions because it involves projectile motion, work energy theorem, and conservation of energy. Awesome. All right, give you a few minutes on 1 and 2. Okay, so for question number 1, we have an isolated system. Whenever they say isolated system, they mean there's no friction. We're not losing any energy, any non-conservative forces, and the law of conservation of energy applies. EI equals EF. Okay, so we're saying the initial kinetic energy is 250 joules. All right, so EK initial, 250 joules. Okay, the gravitational potential energy is 960 joules. Okay, if the crate loses 650 joules of gravitational potential energy, what's its new kinetic energy? All right, what did we say happens to potential energy in this kind of system? It becomes kinetic. All right, so if we're going to lose 650 joules of potential, we just have to add that to the kinetic. 650 plus 250 should be 900, yep. Right, so we should have 900 joules worth of kinetic energy at the end. All right, that's all that question is asking. So you recognize... Yeah, you probably did a lot more work than you needed to. This question is, I mean, and it's fine in the end that you got the right answer, but this is one of those cases where if I really understand the concept, I save myself a lot of time, right? Because probably if you worked it all out, you went to that point and then you probably went, oh, right. That could have been a lot easier. And that's okay, that's your aha moment. You need those, okay? But now we understand it hopefully a little better and we can do it a little quicker. Okay, how many people are done number 2? Okay, do we need more time for number 2 or do we need to go over because we're lost? More time? Okay, I gave you another couple minutes, then we'll go. So for number 2, okay, we're supposed to use the law of conservation of energy to calculate its velocity, okay, and that's for this this mass of 55 kilograms, when it reaches a height of 115 meters above the ground. Initially, it's 225 meters above the ground. Okay, so obviously, by the time it gets to 115, it's going to be going faster. Okay, so what we want to say here is that our initial mechanical equals our final mechanical. Okay, that's going to mean EP initial plus EK initial equals EP final plus EK final. Right? And what we're looking for is part of the final kinetic energy. Everyone okay with that? I'm going to move EP over right now. Right? Before I plug in all the letters and everything, it's just as easy to move it over now. How would I move it over? Subtracting. Okay. So I'm going to have initial potential plus initial kinetic minus final potential equals final kinetic. Now I'm going to put in all my formulas. M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 MV final squared. Okay, they told me the mass. So I can put it in for every M, but M's in every term. I can take it out. Okay? It's up to you whether you're comfortable enough doing that. Most of the time, I remember to give you mass in a law of conservation of energy question. But there have been times where I have forgotten to do that. Okay, like on the test. I give you a law of conservation of energy question and I forget to tell you the person's mass. Most people just go on about their business, no problem. They realize they don't need it and they solve the question without it. But occasionally people will come up and say to me, Mr. Coderre, I think you forgot to give us the mass. And then I chuckle. And I say, okay, that plane has a mass of 10 kilograms. And they look at me strangely, mutter to themselves, swear under their breath, and go back to their seat. Okay? Not realizing, of course, that I could give them any number I damn well please, then the question would work out exactly the same. Okay? It gets even funnier when another person comes up and asks, Mr. Coderre, what's the mass of the plane? 1,000,000 kilograms. Right? And then they're like, oh. And the person who I told 10 is sitting at their desk going, oh crap. He told me 10. Hold on, no. Oh, I'm not going to get this right. What is he doing? He's messing with me. And I am messing with you. Because you should know you don't need it, doesn't matter. But, anyways, I wouldn't do that. It was only funny once, and then it was, like, tragic. It was, yeah. Okay. So, we want to find out what VF is. So, we're going to take out all the M's, because it's easier to do this without that number in there. And then I'm going to divide the 1/2 over here. And then I'm going to what? Square root. Okay, so it's exactly like the motorcycle question we did. So we're going to have 9.81 times 225 plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2. So that's our initial height, our initial speed, our final height. Okay. If we do all of that, we should get our final speed of the mass here. Okay, so okay, so when they get to 115 meters, they should be moving at 58.8 meters per second. Okay. Everybody okay with that? Okay. Now, we're going to end off the day with this question. Like the mother of all law of conservation of energy questions. Because you actually have to remember a couple of things from last unit from projectile motion. Namely, you have to remember how fast a person would be going vertically and how fast they'd be going horizontally at their highest point in the arc. Okay? From a vertical perspective, at the highest point in the arc, how fast is the object going? 0. Which means they're only moving horizontally. And that is something we can figure out. It's the V horizontal that we figured out in the projectile motion all the time. That'll be their speed here at the highest point. And it might be something you need in order to do this question. So, for the human cannonball, they're shot out of the cannon at 21 meters per second, 20 degrees above the horizontal, from a platform that's 15 meters above the ground. The acrobat has a mass of 56 kilograms. What is his gravitational potential energy relative to the ground when he is at the highest point in his flight? So, well, I have to calculate the height. Okay, do you remember how to do that? How to calculate the maximum height in a projectile motion problem? Figure it out, you'll remember. Okay? I'm not going to do it for you, but I'm telling you it's something you have to do. Okay? And then for part B, it says the net is 2 meters above the ground. How fast are they traveling when they hit it? Well, you actually don't need that, the information you calculated in part A in order to do that. It's just a law of conservation of energy question. You could do part B before you do part A. Okay? B is not dependent on A in any way. All right, so give you a little bit of time here to try those two. A is probably the harder of the two just because you don't remember much from last unit, which is sad, but you have to. So, okay, give you a little bit of time on that one.